Hello students. So today we will study chemical kinetics theory part 2. Disclaimer. The images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in the deck and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. Differential and integral form of different order reaction. This is the first topic. Second topic is Arrhenius theory. Third topic is collision theory. And then we will sum up it. Okay. So for first order reaction, the first order reaction is defined as the reaction in which the rate is determined the change of concentration term of the reactant only. So one concentration term means, so basically in the rate law, the power that is given to the reaction concentration is 1. So for the first order reaction, consider a first order reaction that is going from R to P. Then since it is a first order reaction, then we can write rate is equals to change in concentration of reactant by change in time with a negative sign to keep the rate of reaction as a positive value. This can be given as what? This can be given as K multiplied by concentration of the reactant R. Now the important thing here is that we are writing the differential form of equation here. Okay, so this is the differential form of first order. Okay. Now, how can we write the integrated rate equation? So, to write the integrated rate equation, you will simply integrate the differential form. After integrating that equation, what we will get? So, after integrating that equation, we will get T is equals to 2.303 by K log A by A minus X, where T is time, A is initial concentration, K is the rate constant, and A minus X is the concentration of A after time T. So, basically, here what we have done is we have integrated the differential rate of equation and we got the integrated rate of equation this, which is T is equals to 2.303 by K log A by A minus X, where T is time, A is initial concentration, K is rate constant, and A minus X is concentration of A after time T. So how can we write the half-life of the first order reaction? So for that, we can write it as T half is equals to 0.693 by K. So what we have done here is very simple. So we have put T is equals to T half, and instead of concentration at time T, so we have written A minus X. So instead of A minus X, what we have written is simply A by 2. Okay, because the half-life is that time at which the concentration becomes half of the initial concentration. So after putting all these values, we got T half is equals to 0.693 by K. What about the unit of rate constant? So for the rate constant, the unit is given for first order is per second. Now for any reaction, half-life period can be written as how it can be written as T half is directly proportional to 1 by A to the power n minus 1, where T half is the half-life and A is the what? A is the concentration and n is the order of reaction. See, A is what? Initial concentration, n is the order of reaction. Now let us try to write the rate equation for first order gas phase reactions. So consider a gas phase reaction which is about a reactant. So we have a reactant A and it is in the gaseous phase. Then it is decomposing into B and C, in which B and C both are gaseous products. So for that, what we can write, so if you just find the equation for first order, you will find K is equals to 2.303 by T log P naught by 2 P naught minus Pt. What is P naught here? So P naught is the initial concentration and Pt is the concentration. Okay, that is the total pressure, right? So P naught is the initial pressure and Pt is the total pressure after time T. Clear? Now let us move to second order reaction. So what is second order reaction? So the second order reaction is that reaction in which the reaction rate is determined by the variation of two concentration terms. So what we have done is we have taken two concentration term. That means the reaction concentration term will have a power of 2. So its rates equation can be represented as, so this is the integrated rate equation. So it will be given as K is equals to 1 by T x by A minus x. Now what are the terms A and A minus x and x are here? So for one more thing important for this equation is that, so since we are taking concentration raised to the power 2, we can have a different variation also in which we can take two different reactants. And in both the reactants concentration will have the power 1. But this equation is not applicable to that type of equation. Okay, so you got my point. So what we are taking is we are taking a reaction in which it is a second order reaction, first thing. Second thing, there are two reactants and each reactant concentration is having power 1 in the rate law. Then that also will be a second order, but since both of the reactants are different, we cannot use this equation, which is K is equals to 1 by 2 by 1 by T multiplied by x by A into A minus x. So we cannot use this equation. Okay. So what is the rate of rate constant unit? So it is per mole liter per second for the second order reaction. Now, reaction of third and higher order are rare. This is due to the fact that chances of three molecules of combining to a single point simultaneously is very low. So what we are saying is that the probability of trimolecular collision is much more less as compared to unimolecular and bimolecular. Now, why are we considering the collision thing here? Okay, so although we said it earlier that say the order of reaction cannot be determined using the balanced chemical equation, but later on we also studied that it can be determined for a balance from the balanced chemical equation, given that that equation is for the elementary reaction. Okay, clear? Okay, this is the first point. Second point, for that elementary reaction, the molecularity will be the order of reaction. Okay, what is the point? That the molecularity is the order of reaction. So what we can say is that it is same as your molecularity, means the order is same as the molecularity for elementary reaction. So to make the order as 3, the molecularity of the elementary reactions will also be 3, and that is not possible. Okay, that seems to be impossible. Now, sometimes the rate of reaction decreases as the concentration of one of the constituent is increased. So it is also seen that the concentration of reactant can also be, say, having a negative impact on the rate of reaction. So if we just increase the rate of say concentration of that reactant, the order of that reaction will increase, and such reactions are having a negative order reaction. Example will be transformation of ozone into oxygen. Okay, so say we have this reaction 2O3 going to 3O2. This is conversion of ozone into oxygen, and the rate is given by R. So rate is given by minus 1 by 2 dO3 by dt. So we are writing in terms of this equation. Okay, so what we are doing is we are writing in terms of this equation. So you can see here that since O3 has a coefficient 2, so we have multiplied it with 1 by 2, and since O3 is a reactant, that is ozone a reactant, we have put a negative sign. Okay, so deriving this equation, so this is not a this is not an elementary reaction. We cannot write the order directly using the molecularity. So we have determined it. So there is a way to determine it which is beyond the scope of this, say, class. Okay, so they have determined it experimentally, and it is written as K multiplied by concentration of ozone raised to the power 2 divided by concentration of oxygen raised to the power 1. Now if you write it in this way, then you will see that oxygen is having a power of minus 1. Okay, so in this case, the concentration of the constituent is resulting in the decline of the rate of reaction because it has an order of minus 1. Next is pseudo first order reaction. So you must have heard this term pseudo earlier also. Pseudo means something that seems to be real but it is imaginary, right? it is made real by taking or imposing some conditions. Okay, so here what we are doing is we are taking a second order reaction and keeping the circumstances such that the reaction seems to be first order reaction. So when one of the reactant is present in large excess, the second order reaction conforms to your first order reaction. So same thing is written here. So what we have done is we have taken a second order reaction, and by increasing the concentration of one of the reactant, we have made it to look like first order reaction. So it is not a first order reaction, it seems to be a first order reaction, and that is the reason it is called as pseudo first order reaction or pseudo unimolecular reaction. Example, what are the examples? The simple example which everyone reads is the hydrolysis of ester in acidic medium. Suppose this is the reaction that we are dealing with. So we have taken what we have taken. We have taken ester of acetic acid. Okay, so this is what this is ethyl acetate. Okay, this is ethyl acetate, and we have hydrolyzed it in the acidic medium. Then we got carboxylic acid and ethanol. Okay, so this is what this is hydrolysis of your ethyl acetate. Now, why it is called a pseudo first order reaction? Because the rate can be given by K multiplied by CH3COOC2H5. Okay, and it is a second order reaction, but because of the large concentration of water, there is a large concentration of water, because in hydrolysis we often take water in excess amount. Not due to this thing, what it has done, it has made the reaction to be first order reaction. Okay, clear? Now, moving on to the temperature changes. Okay, so what does temperature does? What does temperature does to the rate of reaction? Okay, so it is said that if we increase the temperature by 10 degrees Celsius, then the rate of reaction is doubled. See here. So again, I am repeating it. So it is said that suppose if a reaction is occurring at suppose it is occurring at a rate A at temperature T. So if we just increase the temperature by 10 degrees Celsius, that is T plus 10, then the rate becomes 2A. So that's simple. Now, the effect of temperature is generally expressed in terms of temperature coefficient. Okay. And the value of the temperature coefficient mainly lies between 2 to 3. Okay, so we have said that for each degree rise in temperature, 10 degree rise in temperature, the rate of reaction doubles. So we mean that, so by this we mean that the temperature coefficient is 2. Now, if the rate of reaction triples, then the rate of coefficient will be 3. So it is basically the times the rate of reaction increases when we increase the temperature by 10 degrees Celsius. Now, next is Arrhenius equation. So this Arrhenius equation is also a way to determine the effect of temperature on what? Effect of temperature on this rate of reaction. But the thing that we have done is that we have made the thing more specific. Okay, so initial case we cannot determine it exactly, but in this case it is more approachable and much more what? Much more specific. So let us see what is the Arrhenius equation. So this is the Arrhenius equation given by K is equals to A multiplied by e to the power minus EA by RT. We will see each of these terms. Although we know some of the terms earlier also, so this is the term we know it. It is called as rate constant. And now if we plot a graph between K, that is this, and temperature 1 by T, so we are taking the inverse of temperature, then we will get this graph. Okay, so what we are doing, we are taking the graph between log K and 1 by T, then we got this graph. So you can see very clearly that this graph is having a slope of minus EA by 2.303 R. So you can use this equation to get this graph, right? Just take log on both sides and you will get the equation which will be equated to y is equals to mx plus c, and then in that case you will get your m, that is the slope, as minus 2a by 2.303 R. Again, K is the rate constant, A is the constant, Arrhenius constant or frequency constant, or it is also called as pre-exponential factor. Then EA is your activation energy, so this is your activation energy, and R we know it very well. It is your gas constant, so I have not mentioned it. And temperature is represented by T, which is taken in Kelvin. Now, what it does, it explains the product formation through the intermediate of or activated complex. So, Arrhenius theory is based on the fact that the product are formed through the intermediates or activated complex. So, we will see what is the intermediate, what is activated complex. So, this equation is based upon two theories. So, this equation itself is based upon two theories, which is Arrhenius theory is based upon what theories? Collision theory and your transition state theory. So, what are these theories? So, we will look upon it later on. So, if we know that K is equals to A e to the power minus EA by RT, then EA is always positive. So, this is very, very important that activation energy will always be positive. Questions are asked from here that choose the correct statement. So, questions like this are often asked. So, EA is always positive. And K always increases with the temperature. So, this thing is also very important that for any reaction, no matter whatever the reaction is, the rate constant always increases with increase in temperature. Now, what will happen as a result of it? The temperature will always increase the rate because rate is directly proportional to rate constant and temperature is directly proportional to rate constant. Therefore, your increase in temperature will always increase the rate of reaction. And it will not depend upon the enthalpy of reaction, whether it is endothermic or exothermic, it will always increase and decrease the rate of reaction. It will always, increase the rate of reaction. So, it doesn't matter it is whether exothermic or endothermic, it will always increase the rate of reaction. Now, suppose what we do is we take the temperature as infinity and put it back in the Arrhenius equation. Then that will give 1 by T and 1 by infinity is 0. Therefore, K is equals to A multiplied by e to the power 0. And also we can say that in this case, your rate constant become equals to your Arrhenius or frequency factor. So we can say that what is our A? So A is basically the rate constant at infinite temperature. Now for free radical reaction, EA is equals to 0. So this is very logical thing also. EA is basically the energy required to complete the reaction or move the reaction to your transition state. But since radicals are very, very unstable, they will quickly react and the energy that is required for the reaction is quite low. Clear? And since for the radical reaction, free radical reaction EA is 0, then we can also say K is equals to A. So K becomes independent of temperature in this way. So K can be equals to A in two ways. The first is if you take the temperature as infinity, or if we take your activation energy as 0. Now let us come back to this activation energy and get more idea about it. So I have given you a general idea that it is the energy that is required to proceed the reaction. So basically I would say a proper definition would be it is the minimum amount of energy that is absorbed by the reactant for a chemical reaction to occur. Okay. So this energy is called as activation energy and it is represented by E. In the subscript we write it as A. Question often comes from this activation energy concept. So this is the graph that will make it more clear. So two things are there. We will get to it one by one. So first of all, you can see that we have a reactant which is going to the product. So first we will take the part. So there are two parts. First is with catalyst and second is without catalyst. So first we will try to understand a without catalyst part because the with catalyst part requires somewhat more information. So we are going from reactant and moving on to product. So in this whole process, the reactant energy is increased by this amount for without catalyst thing. So this amount is called as your activation energy. Okay. And then after reaching the transition state, it goes back to the product. So this is called as the activation energy, which is the energy that is required to reach the transition state by the reactant. And the difference in energy between the product and the reactant is called the enthalpy of reaction, represented by delta H. It can be positive and negative both. So in this case, it is what? So you can see that product is a lower energy and reactant it has a higher energy. Therefore, delta H will be negative because final minus initial will give a negative value. Therefore, this reaction is what? it is an exothermic reaction. So activation energy does not depend upon volume and pressure, but it depends upon the catalyst. So you can see here, there are two pathways. First is this and second is this. So in the first pathway, we have a without catalyst reaction. But as soon as the catalyst is provided, what it does? So many students may say that, okay, it may provide energy, but this is not the case. What they simply do is they provide a different pathway for the reaction to complete. So in this case, the reaction goes through this dotted path, which has a lesser requirement of energy. And this is the way in which the reaction goes in the presence of catalyst. Now what the catalyst has done, it has decreased the rate of reaction by this amount. See, this is reduced. This amount is reduced from this to this. And we require now a smaller amount of activation energy for the reaction to complete. And one more thing is that it does not interact with the energy of reactant or product either. Now people all may have got a wrong idea of the catalyst at some times, and they say that they can also reduce the rate of reaction, and they use terms like positive or negative catalyst. So this thing is completely wrong, right? Because catalyst is the word itself which is referred to as something which increases the rate of reaction by lowering the activation energy. So whenever we say catalyst, you should always keep in mind that catalyst is something which increases the rate of reaction. It can never reduce it. Now for this reaction A to B, if your delta H is negative as it is for this case, then it is an exothermic reaction, right? But if the opposite happens, suppose your delta H is more than 0, then it will be an endothermic reaction. Now enzyme catalyzed reaction are faster than the metal catalyzed reaction because they have lower activation energy. So you will see later on that your enzyme catalysis is very fast due to this high specificity and high efficiency. So it provides a very lower activation energy as compared to the metal catalyzed reaction. Threshold energy is independent of temperature. Okay, what it is? Threshold energy is independent of temperature, but EA shows a temperature dependence. How EA shows a temperature dependence? So EA is basically the activation energy. Now if we increase the temperature, that temperature will provide kinetic energy to the reactant and it will move up in the energy axis. That will result in a lesser difference between the transition state and the reactants, and therefore we will have a smaller activation energy. Now how we will calculate activation energy? So activation energy can be calculated by knowing the rate constant at two different temperature, assuming that EA and A remains constant. So this is very important point to note. So if we take two different temperature, your EA will not change because EA is dependent upon temperature, but that variation is very negligible in case of small temperature changes. So we are assuming that your activation energy is same and your frequency factor also remains same, that is the pre-exponential factor. So for two different temperatures, they are kept same. Keeping that in mind, what we do is we take ln of the Arrhenius equation. So if we take the ln of this equation, what we will get? We will get ln k is equals to ln A minus EA by RT. So we have used some simple properties of logarithm to find this equation. Now what we have said that if we have rate constant for two different temperatures, then we can calculate what? Then we can calculate the activation energy. So we have done the same thing. We have taken two different temperatures T1 and T2, and at that two different temperatures we have the value of rate constant K1 and K2 respectively. Then we can write for the first case for temperature T1, ln K1 is equals to ln A minus EA by RT1, because temperature is T1 and your what? And your K1 K is K1 for temperature T1. In the next case, what we do is we take the temperature as T2, and for that case your rate constant becomes K2, and this is your whole equation. So these are the two equations at two different temperatures. Now if we subtract both of these equations, what we will get? We will get ln K2 minus K1, and on the right hand side, that is on the RHS, we will get minus EA by RT2 plus EA by RT1. Or else if we take this term here, then what we can write? EA RT1 minus EA RT2, and that is equals to ln K2 minus K1. Taking your EA by R common, finally we can write, so since ln K2 minus ln K1 can be written as ln K2 by K1, so it is written as ln K2 by K1 is equals to EA by R multiplied by 1 by T1 minus 1 by T2, bracket closed. Clear? Now if you just simplify this equation more, we will multiply both of this and cross multiply also simultaneously, then that will result in T2 minus T1 divided by T1 into T2. Clear? Further, what they have done, they have taken log instead of ln, and ln can be converted to log by multiplying by 2.303. So that can be written as 2.303 r. So when we take log here, so this will become 2.303 log k2 by k1. So we have multiplied this 2.303 on this side, and therefore we got this equation. Clear? Now the important point to note here is that T2 is greater than T1. Now the relation is used when the rate constant are at two different temperatures given. So we know that if we take this equation, suppose dlk by dt is equals to Ea by RT square, and when we plot log k versus 1 by t, we get a straight line which is represented by Arrhenius equation also. So what we have done is we have taken the log of the equation, that is k is equals to a e to the power minus Ea by RT, and then we have solved it using logarithmic functions, and for ln we have put 2.303. Now for this equation we can plot the graph. So this is y, this is mx, and this is c. So y is log k, and your m is Ea by 2.303 r, so that is our slope, and x is 1 by t, right? And what is x plus c? So what is c? It is log a. See, given here. So this will be log a. So this to this part where the intercept happens of this line, this is called as c. Clear? The same thing is written here, that the intercept of this line is equals to log a, as mentioned earlier, and the slope is equals to minus 2.303 r. So therefore we can write in this way also. What? Ea is equals to minus 2.303 r multiplied by slope. So we have put slope instead of all of this. Now according to collision theory, so we have moved to what? We have moved to collision theory. The molecules are considered as hard spheres, and when the molecule collides, we get the reaction. So the collision among the reacting species which result in products are called effective collisions. So this is also very important. There may be collisions, but there are many collisions which will not reduce to product. So we will consider only those reactants, okay, that are not converted. Okay, so what we have done, the collision among the species which result in the product are known as effective collision. So only those collisions are considered which are resulting in the product, while those which are not resulting in the product may be not termed as effective collision. Now the species taking part in the chemical reaction must have a certain minimum energy, which is your threshold energy. So that energy is nothing but the threshold energy. It is not equals to the activation energy. Do not confuse it with the activation energy. It is the whole energy that is required to your energy that is required to reach the transition state. So if you want to write threshold energy, you can write in terms of activation energy. Et is equals to Ea plus delta H, that is your change in enthalpy. Just put see it in that equation, you can get an idea that what I am saying. So we can write, so same thing is written here also. It is activation energy of Ea and average energy of the molecule, that is your reactants. Okay, this is called as threshold energy. Now if we assume that the rate of reaction is equal to the rate of collision per unit volume or per unit time multiplied by fraction of collision, then the rate constant is given by, so what I was saying is that is we are taking the collision theory, right? And we are saying that the rate of reaction is equal to the rate of collision at what rate the collision is happening per unit volume or per unit time, and then we multiply it by a fraction of collision to get the expression, which is k is equals to z AB, where A and B are two different molecules whose collision is to be observed, multiplied by e to the power minus Ea by RT. So this is the collision theory predicted equation, where ZAB is again, so we have said that more the collision will be, more is the chance of reaction. So what we are saying that collision is directly proportional to the rate of reaction. So we have written it here, ZAB is equals to collision frequency. So this is nothing but collision frequency. More is the collision frequency, more is the chance of reaction. So second thing that is to be addressed is the steric part. Okay, so although the molecule can have the immense amount of energy required to do the reaction, but they would not give the reaction. And that will be the case when a steric factor comes into play. So the steric factor should be proper for the reaction to occur, although the energy is much more than enough, right? So keeping the steric factor in mind, we can again write the equation rate is equals to PZAB multiplied by minus Ea by RT, and where PB is what? P is your steric factor or probability factor. if we just look at the summary, what it will be? So it says that the rate of reaction is measure how the reactants get fastly converted into product, and the rate equation is the measure of the frequency of effective collision between the reactant molecule. The order of the reaction is the power to which the concentration is raised in the rate law. So we know it very well. You don't have to discuss about it. Now the number of molecules that participate in the rate determining step is the molecularity. We know it, right? For a complex reaction, we take the elementary reaction, and that is the RD step, and that is your required way to calculate the molecularity. Okay, the number of molecules that participate in the rate determining step is called molecularity. So if the Arrhenius theory states that your rate constant of a reaction is related to temperature, then it is given by the equation. You see it is K is equals to A e to the power minus E by RT. The collision theory assumes that the rate of reaction is proportional to what? It is proportional to the frequency of effective collision, not only the temperature but also the frequency of effective collision between the reacted molecule. Thank you.